Hello, and welcome to this discussion of the physical origins of heat transfer. Right now we're just going to talk about what gives rise to heat transfer in a system. So the first thing we're going to talk about is conduction. Now, conduction is the diffusion of heat through a material. It's also the basis for convection. You need to conduct heat into a fluid before the fluid can then carry it away. That leads us to the next type, which is convection. Convection is then a combination of conduction into the fluid and fluid motion or advection. So conduction plus advection gives us convection. The last type is radiation heat transfer, which is the exchange of photons between two surfaces. Thermal radiation is used by infrared heaters and grills and things like that, and it doesn't require a medium. It can occur through a vacuum. So therefore it becomes very important for space applications. Now, conduction is, of course, energy transport through a material. It occurs any time there's a temperature gradient in a material, and it has two causes. The first is the transport of phonons, which basically means thermal vibrations of atoms and molecules as they bump into each other in the material and transfer energy that way. The second method is transport of electrons through the materials, especially in materials like metals that have a lot of free electrons. They can carry energy, and that contributes to the thermal conduction. So we describe conduction with Fourier's law of conduction, which was proposed by J.B.J. Fourier in 1822. And it basically says that the heat transfer per unit area, which is the heat flux, is proportional through the thermal conductivity to the temperature gradient. Basically, it explains observations with a mathematical relationship. It doesn't really come from theory. It just people collected some data and they found out that this relationship fit the data very well. Now, it has been tested in many systems, so it is pretty reliable. There are some exceptions to this or variations to the rule, but it is a very useful engineering concept. The thing to remember is that it is not a scientific explanation or theory for why this particular relationship exists. Now, the negative sign here is a consequence of the second law of thermodynamics. When dt dx is negative, which means temperature is decreasing in the positive direction, that negative sign ensures that the heat flow is positive. So it basically ensures that the heat is moving from high temperature to low temperature. And then if we integrate this over an area, so we get heat flow per unit area, we integrate over area, and that'll give us the total heat rate. Now, if the surface conditions are constant, then we can just multiply this by area, and that'll give us that total heat rate. Convection, as I said earlier, is due to flow. It's a combination of conduction and advection. So basically what happens is the fluid near a surface gets heated up, but then the fluid moves. So the heated fluid is carried away from the surface and replaced with cooler fluid, and this helps enhance the heat transfer. Now, it's a pretty complex phenomenon, but it's basically due to the development of the velocity, and it really depends very strongly on fluid properties and flow rates and so on. Now, we can describe it simply through Newton's law of cooling. Newton's law of cooling relates the heat flux to the temperature difference between the surface and the fluid through this convection coefficient. Now, actually determining the convection coefficient is a very complex problem, and it's one of the major challenges in heat transfer. We're going to spend quite a bit of time talking about how to find convection coefficients. Values for this convection coefficient can range from 5 to 50 watts per meter squared Kelvin for natural convection with air, from 50 to 500 watts per meter squared Kelvin for forced convection with air or certain oils. Forced convection with water will give you values between 200 and 20,000 watts per meter squared Kelvin. And if you have boiling or condensing flows, the heat transfer coefficient can range up to 120,000 watts per meter squared Kelvin. So it ranges from basically 1 to 100,000 or more. So we have to be very careful about using the correct model to predict it when we do heat transfer calculations. Radiation is due to the emission of thermal radiation, basically photons that are emitted because of the thermal energy of electrons in the material. So heat transfer at a gas surface interface is going to involve radiation emission from the surface. It also may involve incident radiation coming in from another surface, and then the surface may absorb some of that, and it may reflect some of that. And then you may also have convection going on with a fluid. So it's an extremely complex process, and we'll talk about it more later. We predict radiation heat transfer with the Stefan-Boltzmann law. Now, this is valid for certain assumptions. For simple heat transfer equations, we can use it. It was obtained by Stefan in 1879 empirically through measurements, and it was then derived theoretically by Boltzmann in 1884. So it's the Stefan-Boltzmann equation because they both contributed. And it's a useful approximation for a wide range of engineering situations. So here we have the heat flux, the emissivity of the material. Then we have the Stefan-Boltzmann constant, which is 5.67 times 10 to the negative 8th watts per meter squared Kelvin to the 4th. Now, a quick shortcut to remember that is it's 5678, right? 5.67 times 10 to the minus 8th. And then here we have the temperature difference, although in this case, it's temperature to the 4th rather than just temperature. So we have to remember that for radiation, it's temperature to the 4th rather than temperature. So we're going to look at how we can help identify heat transfer process. So we're going to look at the difference in the heat transfer processes between single pane and double pane windows. So if we look at the figure, we're going to try to identify some of these heat transfer processes. So I'm going to blow up the figure. And the first thing is we have several heat transfer mechanisms occurring at once. So we want to divide this heat transfer path into sections that are connected to each other. This helps us break down complex problems into a series of easier problems. So we do that by first looking at radiation. So we have radiation from the room walls to the window. And then we also can have convection from the room air to the window. Then we'll have conduction through the glass. Now here we're going to start to see a difference between the double pane and the single pane windows because there's also going to be convection through the gas that's in between the two window panes. Now, if the window panes are very close together, it may just be conduction because there's not enough room for convection to occur. Or it could be a vacuum, in which case you'd have only radiation occurring here. And then you'll have conduction through the outer pane of glass. And then finally, you're going to have convection with the outside air. And then you're going to have radiation coming in from the sun, so that's going to heat the outer surface of the glass. And you'll have radiation between the glass and the environment, which is going to cool the glass or heat it depending on the temperature of the outside environment. So that gives us a set of heat transfer mechanisms, one for a single pane and one for double pane windows. Now the question I'd like you to ask yourself and see if you can think of an answer on your own is, which one of these windows would you want in your house? And why that kind of window? And what is it about that particular type of window that makes it more attractive for putting it on your house?